Hello, everyone. Welcome to the 18th lecture of CS162 2021. So today we are going to talk about general input-output. And just to summarize, so far, we have studied abstractions, the API which is provided by the operating system to the application to run a process. We talk quite a bit about the virtual memory, demand paging, how to manage the physical memory, and about virtualization. And we also talk about synchronization and scheduling, okay? So, and how to manage the CPU resources and how to synchronize to have multiple processes and multiple threads accessing the same resources and how they can cooperate in order to implement some more complex functionality. Okay. So now one thing we haven't talked as much so far is about input and output. And obviously the input output is a fundamental part of any computer system, because that's how we interact with the computers, through some input output devices like keyboards, mouse, cameras, and things like that. And also this is how the computer itself interacts with the environment and with us. Displaying information on the screen, printing information, and other things like that, right? Now, the biggest problem, and this is what also makes this lecture a little bit maybe harder, is that there are a huge variety of these input-output devices. Right. Actually, if you think about others like memory is pretty simple. It's an array of addressable bytes, right? That's pretty much what it is. If you think about the CPUs and so forth, from our perspective, it's a resource which we want to probably time slice in time slice. So then we can visualize it. So we create this illusion that every process has access to its own machine, virtual machine, right? And but if you look about input-output devices, this is a huge variety, and not only in terms of the sizes, not only in terms of the speed they operate at. You can have networking which is hundreds of gigabits per second versus keyboard, which is 1 character per, whatever second. But also in terms of reliability, in some cases, you can lose information, like packets on the network can be lost. So you need to recover. So in all aspects, in all dimensions, you have a huge variety. And yet the operating system needs to cope with this variety in a reasonable way. Right? You don't want to be exposed. And what that means, you don't want your program, when you are developing a program, to think about each of these input devices in a different way, right? And this is the role of the operating system. Again, despite this huge variety, to provide us with an interface which is reasonable, which is scoped, and you can make sense of it, and you don't need to think about different concepts, or you are going to operate on different IO devices. Okay, and this is if you remember, this is a figure we have shown a few times in the past, and here this protection boundaries, which is down here, it's also abstracts away this input-output devices. Okay. So today we are going to talk about how you are going to get the input, how you are going to get this kind of input from these devices, and eventually where do you need to get this input? This input from these devices you need to put in memory, right? Because why? Because your program, in order to operate to the input, it has to find the input in memory because the program operates only on data in memory, right? And that's pretty much it. Now, this is one example, and this is an old example, many years back. And this is from Sun Enterprise. Again, Sun, it was a big company of workstations, and it was acquired many years back by Oracle. But in the heydays, this was a great company. And if you think about the devices and only looking in terms of the speed, you have keyboards, like I mentioned, and the system bus. The system bus, we're learning the system bus on the machine, which connects different devices which are in the same enclosure on the machine, like, for instance, disk storage and things like that. There are difference is 2 orders of magnitude. So you need to provide interfaces which can cope with such a huge variation of, in the speed. Okay. So this means that, and you need to have something which works very well when you have high throughput. So the overhead for transfer per byte should be very low. At the same time, you shouldn't, if it's something very slow, you shouldn't just waste time waiting for the slow devices, right? It's like if something happens 1 per second, you cannot wait once, for the entire second to get 1 character. Okay. This is another way to look about, and this is to put everything in one picture about what we learned so far and what we are going to learn today. Right on the left-hand side, you have the processor, and the processor obviously has the CPU, but in addition to CPU, has some storage, right? And the storage comes into registers, then a bunch of caches, L1 and L2 cache, these are per core, and then you have an L3 cache, and the L3 cache typically shared across multiple cores. Right? And then you have memory and secondary storage and maybe another tertiary storage, or and so forth, right? And the difference between this kind of storage hierarchy, it's obviously like going from registers all the way from this to disk storage. You have at each level, it's much larger capacity, but also higher latency. Right? So we learn about that. And we learned that about caching, we learned about demand paging, and so forth. And in addition to that, here on the top with the yellow, you have all these devices, which again needs to be available, the data which is read from these devices to be available to processor. And then for the processor to write data to these devices, like to storage, to screen, for you to see an image. And typically all these devices they have a controller. And this controller, it's what the name implies, controls these devices, because these devices are different. In some sense, this yellow box provides this magical interface, which is reasonably uniform across all the devices to the processor and to the programmer. But in the back is doing this heavy lifting to uniformize these APIs by dealing with such a heterogeneous set of devices. Okay. So now let's look a little bit into more details to see how things are on a computer, right? And this is what you have on your computer. This is actually on your laptop or iPad. At some level, this is what you have, okay? And you have a processor, obviously, and you may have we may have a GPUs, you may have a network card here, Of course, you have some storage devices. You may have speakers, internal and external speakers. You may have printers, of course, the keyboards. You have the monitor and many more, right? So again, you need to take all this information from these devices to get in to process and then to write back information, at least to some devices, to some of these devices. Of course, you don't need to write back information to the keyboard. Keyboard is only an input device, and the printer is only an output device, right? And how do you connect them, right? So first of all, how you wire them. So it turns out that the way you wire them is through this bus. You have a bus, right? So everything goes to a bus, everything, including actually even the memory on the machine. And the data is sent through this bus, okay? And this is how you get the data into the processors. This is how you get the data out of the processors, through one bus. And more precisely, what is a bus? It's represent the set of specifications. It specify what are the wires, how many wires they have. It has and how you connect to it, and then on top of that, it has to provide an API. Read, write. How do you read and write from this bus? And you also have how you are going to address a particular device. And for the particular device, you also have not only data, reading data, but you have also control data, right? Like for instance, for a disk, like we'll see, you need to tell the disk where a particular block is on the disk to read or to write. Right? This is happening to the control lines, right? And the controller, like you see the yellow box, is going to decide and instruct through using the control line a device what to do and where to get the data from or to write the data to. And then there is also the protocol. You have multiple devices which are going to send the data on the same bus. So what do you need to do, right? Not all of them can send the data at the same time, right? In general, you have only one device being able to send data on the bus at a given time. So this means that you need to arbitrate. If more than one device want to send the data on the bus at the same time, then you need to arbitrate who is going to be allowed to send and who is going to wait. Okay. And okay, and of course, you are, the devices here are, which are, again, remember about, they are very different in speed. The devices which are, close to the processor, like memory, like things like that, they are very, very fast. The ones which are very remote, like are much slower, say, keyboard or printer. So now, why a bus? This is very important. It may seem that this is obvious. Of course, it's a bus, right? But think about what is the alternative. So an obvious alternative here, it will be to connect every device to the processor, right? And if the two devices have to communicate among themselves, you're also going to connect between them, right? The problem is that then you are going to have, in the worst case, you have n devices, and you can have n square connection. Right? You don't want that. It's very complicated. Okay. So that's why what you want, you have this bus and everyone is connected to the bus, and then it's beautiful. Then you multiplex the bus in time. But the problem is that if you multiplex in time, then it may be very inefficient, because remember, all these devices have very, very different speeds. So like for instance, if I'm going I'm going the keyboard, right? It's like a key, right? You click a key and it takes, again, it's like every 1 second. It's very inefficient way of that bus, right? Because in the same time you may send, if from memory, you can send hundreds of gigabits per second, or which means a few tens of gigabytes per second. Okay, so it's very inefficient. right? You don't, if you have slow devices, it's very inefficient for very fast devices, okay? And so that's one of the big problems. Advantage against simplicity, everyone connects to it. The standard bus today is PCI, is called Peripheral Component Interconnect. And it started as a parallel bus. Parallel bus meaning that at one device at a time is going to be able to send data, and it can send data in parallel. If it sends, and the width of the bus represents how many bits you can send in parallel. So for instance, if you have 128 bits, this means that you are going to be able to send in one clock cycle 128 bits, right? And you multiply this bus like we discussed. But now the problem, if it's a slow device, then you are going to use, and also it sends only 8 bits while the bus is 128 bits. You are going to waste 120 bits while this device is alone using the bus for sending just 8 bits. Okay, so I'm going to stop here. Any questions about so far? Okay, so this is a little bit, again, it's like very descriptive, a lot of heterogeneity, so maybe a little bit boring, but it will change. So now you may have heard about PCI Express bus. So what is this again? The problem is that it's parallel. This is great. It's simple, but only one device can use at the same time. And if it's a slow device, you waste so much time for the fast devices. So PCI Express is pretty smart. So it's no longer a longer parallel bus. You still have multiple lines, but they are serial channels. And you can, now a device can choose how many lines it's going to send, to send, right? So for instance, if you have a very slow device like the keyboard, right? You can use to send everything on one line, right? And you leave all the other lines for others, like memory, right? Access to memory or to storage. Okay. So this allows the slow devices to share the PCI bus with fast devices in an efficient way. And again, the beauty of this of Linux and Unix behind it, before it, was that the ability to support all this, not only to migrate from PCI to PCI Express, but again to provide a pretty uniform interface across all these devices. Okay. And also the API itself remains the same, pretty much the same. And this is quite amazing, right? If you think about it, because Unix, when it was designed, Unix, I mean, a lot of things you have today, maybe they are not available then. You didn't have GPUs, for instance. I'm sure you didn't have a lot of this kind of game, game inputs devices, right? And many other things, right? So despite that, we started to connect things to the computer, which are not envisioned when people designed the operating system in the first place. The operating system was still being able to preserve the same API. Of course, you need to implement controllers or drivers, which are going to provide, to support these devices and provide the same kind of abstraction like before, right? We'll talk more about that. Okay. Anyway, here is an example of the PCI architecture. Today, you have a PCI number 0 PCI number 0 here. And this is very fast one. This is connected to the CPU, and the CPU is also having a memory bus to the RAM. Then there is a PCI bridge here. You have another PCI bus. This PCI bus is a little bit typically slower, and this is connects the storage devices, for instance, a scanner, and all the webcam, mouse, and keyboard. And then you have another bridge here from PCI to ISA. So ISI, it was an older bus standard. So you may still, you still have devices, for instance, hard disk drives, which implement this standard and to connect to this ISI bus. And this is a bridge, so then you can use these devices on a PCI architecture. Okay. So here, let's go into a little bit into a little bit more detail. So how does a processor talk to all these devices? Okay. So here is a CPU, and you have the memory, and you have a memory bus here, and now you have this is connected through a bus adapter to get data from this device controller, right? Remember, each device has a controller. And to the device, you set the instructions about what data to get or to write. And the controller is talking with the device to get what the program asks for. Right? Now, within a device controller is quite complicated. Actually, many device controllers, they have their own processor. So it's like their own computer, right? They have ARM processor and so forth to implement the program which is going to control that device. Of course, you have a bus interface to send the data in and out to connect to the other buses in the system. And it has a memory. You can, for instance, for doing for caching data, right? For instance, when you send data to the printer, you can assume that it's not like you send 1 byte is printed, you send 1 byte is printed. No, you send a lot, almost the entire file, or you can send the entire file, which is kind of stored, at least part of it, in local memory, and then it's printed from there, right? And then this is very important. You have a set of registers here, which are, these are the registers to which they are used to interact with this controller. They are used to tell the controller what to do, right? And, you know, read, write, or configure the controller in a particular way. It's also to get the status of the controller. The status of the controller can be busy, right? The printer is busy, right? Showing the status, not sorry. This is the status of the device controlled by the controller. Okay. Another important thing, if you remember, we have this kind of interrupts, right? You remember about the interrupts? And one of the main uses of interrupts is to react when something happens in the external world. And one of the main use cases there is about when you have some data to get from a device, from the network, for instance, or when some device needs attention. Right, so that's what the interrupt controller, and the controller is going to raise some interrupts, and the interrupts are, if you remember, the operating system, depending on the interrupt, is going to have an interrupt handler, which is going to handle that interrupt. Right, the network card has, and a network controller has new data, is going to interrupt, to raise an interrupt. The OS is going to handle that interrupt and is going to read the data from the controller. Okay. Now, how do I interact? How do I program these controllers? There are two ways: port mapped I/O, in and out instructions. So basically here for the Intel architecture in particular, you have say out 0x21. So this is an address. This is an I/O. So each I/O has its own address. Each I/O device has its own address. And basically out 0x1, AL means that the content of register AL is a register. So the content of that register will be written on that output at that address to that output. It will be written to that output. And you have the corresponding in and from a particular port address, and then the data from that port is going to be written in register AL, for instance. Okay. So you have special instructions here, right? And special addresses for these devices. On the other hand, you can have memory mapped I/O. And this is pretty cool. You basically reserve or you configure some addresses in the memory, in the RAM. Okay. And these being are connected to these input output devices. Okay. And then the only thing you do, you use load and store because it's memory. Load means if I'm going to put the data there at that particular address, that data is going to be sent to the corresponding device, right? If I read the data from a particular address, which is memory mapped address, then I'm going to read data from the corresponding device. Make sense? This is an example about memory mapped, right? And this is really used for graphics, right? So typically, here, what you have is that, like your screen is a bitmap, right? You know that, right? So the screen, the controller of a screen, sees the same memory, have a region, you devote a region of your RAM, you devote to the screen. And when you are going, when you are going to modify this memory, what you modify, you see immediately on the screen. Right? And so from here, display memory is from this address, 800, whatever, 10,000 to 800, 8,000, whatever, F000. This is a display memory. In addition to that, you may have also a command queue, because you may have, you can provide some commands to the display, for instance, because you may have higher level abstractions rather than just writing and reading, writing individual bits. Like for instance, generating triangles, right? You are going to basically give a command to the controller, and the controller, which is a graphic card, is going to generate this kind of, say, triangles to create much faster, to render much faster some, impressive, objects. Okay. Okay. So this is one thing. So again, in summary here, in this very simple example, you are going to have a region on the RAM, which is seen both by processor and is seen by both, and also by the controller, the video controller, right? And when the processor writes to this address, to this memory, you see it on the screen, right? Okay. So, any questions? Now, it turns out that today, with this, everyone knows about GPUs, graphical processing units, and the GPUs, they have actually their own memory, so you don't have this sharing. And the reason for that, because the memory thing because the memory, if the GPU, if the memory is on the GPU, that is much faster. So you can, render much faster, much quicker. That's one of the reasons. This is for you to know. Okay. And of course, you can protect these memory regions using address translation, like we know. Now, here is an interesting thing. So far, I told you how it's, that you have this processor and you have all these other storage devices and IO devices around it, and they are connected by the bus. But if you look in the processor, into a processor itself, you see some similar things, because in a processor, it's not a monolith. In a processor, remember, you have multiple cores, you have multiple caches, and so forth. So how, and actually many CPUs today, they also have graphic unit, right? Or neural unit, right? Like some of the Apple chips have, right? So, and then how do you connect those? Well, the answer is through a bus, right? Okay, so it's like what you see there outside, outside the CPU, it's also pretty similar inside the CPU. You have different components, like here are a few examples, like I mentioned, and they are connected by a bus. By the way, HGX is a software guard extension. So this is basically, it's a software, it's a hardware enclave for people of you who for people who took a security course, a class. And then you are going to connect outside the CPU. You are going to connect to the memory. DDR, this is the memory. And you are going also, you see here, you are going to have a PCI Express, right? This is how you connect through the PCI Express to the rest of IO devices. This is another way to look at. This is again Skylake system configuration. This is the same GPU here. It's pretty old, but the ones today are not very different. Okay, and you have here basically, you have this is a core, and this is connected to memory. Then you have this PCI Express. It's again to directly connect to other IO devices. And then you have this bridge, and you have another chip which connects to other IO devices. And this typically says these are a little bit slower devices in general, right? USB, audio, video, LAN, and so forth. So it's again the same picture, emphasizing this pattern of multiple components being connected by fast buses. Okay, any questions? So now I mentioned to you that one of the beauty and the successes of Unix and Linux, obviously, is that they were able to provide an API which remain pretty much the same over time, despite a proliferation of IO devices. And the reason for that is because obviously they got abstraction right? And they already recognize early on there are different type of devices, and they are going to handle with these devices slightly differently. So how these devices are segmented? First, is data granularity. When I'm going to read and write from a device, what is the granularity of the data I'm going to use? Lowest granularity is like byte. In some cases, there is bit, but it's rare. It's byte, right? You read 1 byte at a time, you write 1 byte at a time. But there are other devices, many other devices where you write at a higher granularity, like a block, like to disk, or reading or writing from a disk, or reading or writing from the network. It's a level of granularity, it's a packet. So now let's make a little bit this class more interactive. Why do you think that, why byte is not enough? Why not just have the ability to read and write only at the byte granularity? Anyone can tell me? It's exactly Ruthman. Yeah, and Akshay, and this is correct. So if you write and read as a byte granularity, then you need to, this means if you think about from the perspective, this is an API to the application. And I want to read and write a byte. This translates to a system call. A system call translates to a context switch. So the overhead, right, to read and write a byte is non-trivial, right? You cannot sustain, keep up with very fast IO devices, okay? So that's the reason. So byte is fine for keyboard, right, entry. But it's not going to be fine for sending, data at 1 gigabit per second. Because the fixed cost of send operation or receiving operation is too high. Okay. But they got it right from day one because they have to support the disk. Okay. And the disk couldn't do it efficiently at byte level, so they have to have blocks. Okay, good. Access pattern, sequential versus random. Some devices must be accessed sequentially if you have a tape, and others are randomly. Also, there are devices which are under this access pattern. Beyond, it's like, are you going, and we are going to talk more about that. Do you need to monitor that IO device all the time to see what happens, or you are going to get interrupts when something happens, right? Like with a keyboard or network card. But now let me ask you again, it's like, for instance, about sequential versus random. Why not have only one? Forget about tape for now, right? Remove tape, because that with tape is obvious, right? It's like, it's that, you have to access data on sequentially. But even without that, tell me, why not have random, right? Because if I have random access pattern, then it does make sense. I mean, I can emulate sequential, right? I start from 1, and then I say 1. Now I want to get 2, 3, 4, 5, 6 bytes, 3, 2, 3, 4, 5, 6, right? After all, in memory, I have only random access. I don't have sequential access. So why sequential access? Why not random? Yes, Michael, yeah, it's good. We'll learn. Because the random may involve some non-trivial overhead to locate that random piece of information. That's why, like we'll see with the disks. And therefore, if I am going to store the bytes and I can read or write them sequentially, it's going to be much, much faster. So you see, in both these cases, you can get away, only have read writes at the level of byte and only accessing randomly. But you are going to leave a lot of performance off on the table. So block and sequential, block granularity and sequential access pattern, one of the main reasons they are used is for performance reasons. Okay. And now the transfer mechanism. How is this? Program I/O or DMA, direct memory access. Program I/O means the processor takes a byte from one device and transfer to another device. Like for instance, takes a byte takes a block of data from the disk and put it in memory. Right? Using in, out, and load store. It's simple. You can program everything through the computer. The disadvantage is that you are going to use a CPU for doing that. You are going to consume these resources, just moving the data around, not doing useful work. The second way is direct memory access. And now this is a smart one. In this case, you say you are going to deal with two devices. And basically, you are going to tell one controller from one device, well, you have to transfer the data directly to this other device. This CPU is going to send instructions how the transfer should happen. But then the transfer happens between the devices without the CPU being involved. And here is an example. And typically, this is one of the devices is typically memory, right? And here what happens, right? So you have a PCI bus and you have a memory. And here you have a disk. And I want to transfer the data from the disk to the memory, to read the data from the disk into memory. Okay? So these are the steps. The CPU number one, the CPU is going to, the program starts to say, I want to read the data from the disk. Now, under the hood, the OS is going to handle that and is going to send a message, control message to the IDA disk, the disk controller, telling it, okay, you need to get this data to this address in the memory, right? Address X, right? Now, the controller is going to tell this, okay, I need I was instructed to move this data, to transfer this data to memory, to this address X. And now the DMA is doing the rest. The DMA, not the CPU, is going to handle the transfer from the disk controller to the memory, right? So the DMA is going to read the data from the ID and then drive the data on the CPU bus to the memory. Once the transfer is completed, the DMA is going to send an interrupt to the CPU telling, I'm ready. Any questions? Pretty cool, right? So when do IO devices are notifying the operating system? Right? Two reasons. When it was, well, the OS, think about from the OS perspective, what do you need to know? On one hand, you need to know if you are instructed, you have instructed a controller, IO controller to perform some operation. You want to know when that operation, when that operation has completed. The second is if there is an error, right? Okay. So, and like we mentioned, one way to handle that is IO interrupt. Whenever there is one of these events that OS needs to know about, the IO controller raise an interrupt. Okay. Why this is good? The CPU doesn't need to worry about. I'm going, the CPU is going to, the IO controller is going, or it's going to let the CPU know when something worth knowing happens. Right. Also, you can handle unpredictable events, like a new packet arriving on the network. The disadvantage is that the interrupts are expensive. It's a context switch. And when the CPU, when I raise an interrupt, maybe most likely a user process was executing. So you need to do a context switch to go to the operating system, handle the interrupt, and then to go back in the user mode to continue running the process. Right? The other one is polling. So this is the operating system periodically check a device specific status, say, to see whether it's ready, right? Remember that, I showed you in the IO controller, one of these registers was called status, right? So for instance, it's going to be a printer. The OS wants to know when the printer is done, when the printing is done. So I can tell the user, okay, the printer is done. Whatever you send to the printer is done, right? So in that case, the controller has this status register and it's going to be updated when the printer is no longer busy, when file finish being printed. And then the OS is periodically going to check on that. And when it's no longer busy, it's going to tell to the application. Okay. Now, the pro here is low overhead because the OS is going to check on this between context switches. It doesn't need to do a context switch just to check. It's when the operating system gets, the kernel gets control, it's also going to check this, right? Now, the cons is that you check and nothing happens, then that's wasted time, right? CPU cycles, okay? So now, typically you combine those. There is no right solution. That's why you do both of them, right? If you do only one solution, why would have I told you about both? But let me take a step back now and ask you, when are you going to use IO interrupts? And there is a little bit of an answer here, but I just want you to give the answer in your own words. When do you think you should use IO interrupts? When do you think you should use polling? Give me another. This is one example you have here on the slide. Give me another example. Let me ask you, keyboard, right? Are you going to use polling or interrupts? Human IO for interrupts. Okay, that's good. Why is that? Why human IO for interrupts? Rare and slow, and you see here, oh, sorry. Unpredictable, right? It's unpredictable. If it's something unpredictable, it doesn't mean it makes sense to poll forever, right? For something rare to happen. Yes, Gilbert. So you interrupt for infrequent syncs, polling for stuff we need to continuously check. Yes, or if something happens, yeah, this for polling is someone, you say this for polling, sometimes actually you don't use, we'll see, but it's not necessary that you are going to pull the disk. Yeah. So yeah, for the keyboard, eventually, you know, it's again, you have to use the interrupt because this is to tell the operating system when some keyboard is pressed. Because if you watch a movie, you know, for 2 hours or whatever on your computer, you don't type anything, right? Or Zoom, like right now, you right? You are listening to this lecture, right? I hope that you are not doing a lot of many things other than listening to the lecture. But still, right? It's like if you are listening, you don't touch it, you don't touch the keyboard. So it's very rare even. Doesn't make a lot of sense to pull. When you pull, when one of the things, the reason you pull is like in this example, when things happens extremely frequent, right? Once you get, for instance, a packet here, you get so many other packets one after another. You cannot afford to have a context switching per packet. When the context switching is, the overhead of context switching is larger than the time between the events, it probably doesn't, it's not worth to do context switching. It does it not means it's not worth to do interrupts, right? Right. Let me put it in another way. So say context switching, it's 1 millisecond. I'm picking some random number, right? And then say an event happens every 10 microseconds. It makes no sense to do interrupts per event, right? You just pull to see, you know, for that. Okay, very good. So this is a structure in the kernel for the device. So you have the system call interface. We'll talk more about them. And you have some, you know, for memory, for this is what we learned, you know, we have process management, memory management, file systems, and then you have this device control. This is for IO devices, and then networking. Networking typically is different enough, so the API also for networking is slightly different. Okay, so the device control, what it's when we say, you know, so the device control, the controller for the device, this is typically implemented on the device itself. But this device now has to also interface with the operating system. The piece of software which bridges the operating system API with the controller API is called device driver, right? And it's a piece of code which runs in the operating system, in the kernel. Okay. And this piece of code, it implements the Unix IO API. What is that API? Well, this is a thing which survives so many decades. Remember, open, close. In order to communicate to a device, you open, you close. Then read and write. And you can read as a block granularity, you can read as a byte granularity. And IOCTL, IO control, this is a escape patch. Because each device can have, you know, is a little bit different, requires a little bit different configurations. This is what is IOCTL is. It's more for device specific control. Okay. Now, the device driver has two halves. One, which basically is executed in the user mode, and the other one, which is executed in the kernel. right? Sorry, I'm sorry. Both top and half, bottom and half of the device drivers are executing in the kernel. The top one, it provides, it helps to provide the kernel IO API for the which is used by the user program to interact with these devices. Okay, so let's see what happens. So let's say you have a user program and request an IO operation, say to write data to the disk. It's first of all is that is the request already satisfied or something like that, right? It's like this happens when this happens. This happens, for instance, if I am going to read some data from the disk, and when I read the data from the disk, the granularity at which the data is transferred from the disk is larger than what I read. Say I read only 10 bytes, but when I'm going to transfer from the disk, I'm going to transfer one page, is 4 kilobytes. So this 4 kilobytes is already stored in memory. So now I am just going to, if I read the first 10 bytes, then I can read the next 10 bytes. They're already in memory. So I don't need to do invoke to touch the device again. But let's say now is not satisfied. So now I'm going to send the request to the device, right? And well, send the request to the device driver. The device driver is looking at the request, and from here on, this code, right? It's device specific. Okay. I process the request, and then you send it to the device hardware. So this is the device hardware. This is on the hardware, right? So this part, it's on the kernel, in the kernel. This part at the bottom can be in the device driver, right? In the device, sorry, it can be in the device itself. And the device, the controller, is going to execute the operation, say, for instance, instructs the disk where to read the data from, then reads the data. Once it reads the data, it buffers, it sends an interrupt, sorry, and the interrupt is sent to the kernel. The kernel is going to handle this interrupt, is going to get the data from the device, and then is going to see whether the IO is completed. And if it's completed, it's going to let the application know. Okay. Sounds good. Okay. So the goal of the IO subsystem, so IO, it's again, is to provide this interface, uniform interface. And so that a uniform interface means, so uniform API means that the code you wrote for one particular device should work potentially with very minimal changes for other devices. Okay, so for instance, for this code, right, this switch opens some code and then prints some output. It works on multiple devices. It works on this terminal, right? If FD is a terminal, the file descriptor is a terminal. It works from the disk if a file descriptor is a file, right? And it can also work on the printer. The same code. Okay. So now let's talk a little bit more about this this interface and why the interface has been so powerful and so general. Like I mentioned to you, you have block devices, and for these block devices, you write the data as a block granularity, and you have an open, read, write, and seek, right? Then you can have character devices, and this is the level you read and write the data at the level of of a single character. And for this, you have also open read, but you have also, for getting a single character, you get and put API. And then for network devices, this is different enough that you have a different API, slightly different API. You still have open and close, but you have the concept of sockets, and you still have reads and writes. Read, write, and open and close. All of them are still, you still have those. But in addition, you have other richer API. If you remember, you have connect, you have accept, you have also something else, which is select. Select is when you are going to listen on connection from multiple computers. We are going to learn more about that. But these are the three standard interfaces provided by the operating system, and each of the devices falls in one of these categories: block device, character device, or network device. Next, how you are going with respect to timing. How do you interact with the devices? Well, there are few ways to interact. One is a blocking interface. The blocking interface, when you are going to perform an operation, you are going to wait for that operation to finish. Right? When you request, say, for instance, when you read some data, you are blocking until the data you requested is available. Then is non-blocking interface. You just write some data, and the call returns immediately before the data is written. Okay. Now, so this is obviously, you don't know the result, but then you don't block, so you are very efficient. You don't waste cycles of the CPU. And then it's a synchronous interface. And then this basically says, I am going to request the data. And by the way, here what you need to do, and let me know when you are done. So I wanted to read the data, and you need so read the data from this device, and I'm telling you that you need to put the data after this address in memory. Okay, and you put that in the address in memory, and you tell me when you are done with it. This is a synchronous interface. Okay. So some announcements. Unfortunately, next week will be quite a week for you. So the good thing is that after the following week, after the next week, is going to be easier, and the Thanksgiving is coming soon. But yeah, next week will be hard. You have a homework for midterm 2. The review will be on Monday. The time, we are going to let you know the time. The midterm will be on Wednesday between 7 and 9 p.m. Pacific time. The project is due on at the end of the next week. And tomorrow, unfortunately, yesterday, I had, like I mentioned, a flight which was canceled and then rescheduled. Between 11:30 and 12:30, I'll have my office hour. Okay, let's move a little bit. We have another 15 minutes, so let's move quick now. Storage devices. So storage devices are where we store the data and persistently, right? They typically have much larger capacities than memory, but they are slower, right? And we have magnetic disk and flash memories, right? There are two types. Magnetic disks are, these are traditional ones. Flash memories are newer, but now are dominant. They are more expensive. They provide better performance. That's kind of the way to look at them. These are some examples. This is the disk drive. right? You see here a platter, you have here the heads which read and write the data, and then you are going to have, here is another hard drive. This is the heads. You have multiple platters on which you write the data, and therefore you have heads on each platter, for each platter. And here it's micro drive, this is SSDs, right? Now, just to give you a sense, the first IBM personal computer, which was released in 1986, so that was 35 years ago, right? It has, the hard disk was $500. It was 30 megabytes, not gigabytes, megabytes. The seek time is how long it takes a random access. It was 30 to locate, to write the data randomly or read the data randomly was between 30 and 40 milliseconds. And the speed, the maximum speed of transferring the data was 1 megabyte per second, okay? So how it looks like, this is how a hard drive it looks like. You have the platters. The platter has two surfaces, the up and down surface. So you can write on both of them. On each of them, you are going to have tracks, and the tracks are divided in sectors. So the sectors stores a block. And this is a unit of storing, reading, and writing data from the disk. And that is written, and the reads and writes are performed by the header. Okay, so let's now show this one by one. This is a sector. Okay, so you have this ring of sectors. This is a stack, and then the corresponding tracks on all platters represent a cylinder. What is important about cylinder is that the data from a cylinder can be written and read without moving the heads, because the movement of heads, which is called seek operation, is expensive, right? Okay. So some numbers, the disk track, the tracks are around 1 microns wide. And this is very small. The wavelength of light, it's only half a micron. Resolution of human eyes is 50 microns. So you have typically 100,000 tracks on a 2.5-inch disk. And you have these tracks in general separated by some guard regions, because you don't want to write on a track to influence the bits on the others and corrupt therefore the bits on the nearby tracks. Now the tracks length varies, right? The one which are closer to the edges are more are larger than the one at the center. And so typically we are only using half of the radius, only the tracks at the edges of that, because you have more space to store information. If you store it too close to the center, the sector is too small. You are going to get a lot of errors. And disks are obviously huge right now. There are terabytes in terms of capacity. So in general, only a small part of this data which is stored on the disk is active, read write. The rest is used for being archived. And this is important. Before, in the early days, you archive the data not on the disk because the disks are expensive. You archive the data on magnetic tapes. One note, this is more like a footnote. There is something which is called single magnetic recording. And in this case, instead of having a guard between the tracks, you remember that I told you that between tracks, you have the guards. So you avoid writing, when you write on a track a bit, to influence the nearby tracks, right? But in order in the race to add more and more bits to increase the capacity of the disks, people came up with this technique, which actually, in some sense, the tracks kind of almost overlap. And obviously now you need to be very careful and you need to have much more complex, digital signal processing techniques in order to make sure that you avoid a bit being corrupted by writing a bit in a nearby track. So magnetic disk, it's again, you have the heads, cylinders, sectors, and tracks. And now let's see what is the time to read or write data. Okay. So first of all, this is how the architecture looks like. So the disk actually has a controller, right? Like we mentioned many times before. And you are going to get a request, right? The controller gets a request, right? And let me just to show you where this request is coming from. Is here. You see the request. This is the request. Okay. And here we are talking about this device hardware. Okay. So you get the request, and then you have a queue because multiple applications can request data to read and write data from the same time. So you need to queue this request, right? And then you have the hardware controller, which is going to take requests from this queue and is going to satisfy this request. Now, a request, when you satisfy the request, what happens? You need to figure out and assume that you already know where the data you need to read and where the data is located, right? And in order to, once you do that, you need to move that, you need to identify, what do you need to identify? You need to identify a sector. A sector means to identify the track, right? In order to get to a track, you need to move the disk, to move the heads. The overhead to move the disk is called seek time. Then once you are above the corresponding track, you need to wait for the proper sector to come under the head so you can read and write. This is the rotation time. And finally, the transfer time, the time to read and write the information from the sector. Right? Here are some numbers from some other magnetic disks. Is a space is like 14 terabytes. It's pretty, 8 platters. Typically, the seek time is 4 to 6 milliseconds. This rotation speed, rotation per minute is like between 3,600 and 7,200. There are also some of the new, faster disks at even 1,500 rotation per minute. Average latency of rotation latency is between 4 and 8 milliseconds, right? This is, if it takes 8 milliseconds for a full rotation, then on average, you need to wait for 4 milliseconds rotation latency in order for the sector you are looking for to come under the disk and under the head. And transfer time between 50 and 250 megabytes per second. The transfer, a sector is typically between 512 and 1 kilobyte and things like that, right? They used to drop, because the cost used to drop by a factor of 2 every 1.5 years is no longer true. So now let's go through this example. So assuming that we ignore the queuing and the controller times, okay? So we ignore this queuing time and the controller time. Let's look only on the media time. Assume the average seek time is 5 milliseconds. Assume that the rotation, speed is 70 to 100 rotation per minute. So this means that it takes 8 milliseconds for a full rotation. And the transfer rate, assume, is 50 megabytes. Then the transfer rate of 15 megabytes per second, if it's a block size of 4 kilobytes, right? So assuming the transfer rate is 50 megabytes per second, if the block size is 4 kilobytes, then it takes 0.08 milliseconds to transfer one sector, right? You divide 4 kilobytes, the size of a sector, on the transfer rate, right, to get that time. So then reading the block from a random place on the disk, you need to seek first to the track, you need to wait for the sector, and then you read it. So it takes 9 milliseconds, a little bit more than 9 milliseconds. Is equivalent to 450 kilobytes per second speed, transfer speed. If you read the block from a random place in the same cylinder, then if you do that, you don't need to incur the seek time. So now the latency is only 4.08 milliseconds, which means that the data now rate is 1 megabyte per second. But now assume that you just need the same next sector on the track. You sequentially read. Then you don't need to incur the rotation delay either. So it's 50 megabytes per second. So it's 50 times bigger or 100 times bigger if it's purely random. So now you see why you have seek. Also, you have sequential access and versus only random access, right? If you can sequentially access the data, it's so much faster, at least for the disk. So the key to use a disk effectively is to make sure that you, as much as possible, you access the data sequentially, okay? So now there is a lot of intelligence in this, embedded into this controller. So the sectors, for instance, you have sophisticated error correcting codes, right? Because, to avoid data corruption. And this is very important because if you store the data on a disk and you trust that disk because it's stored persistently. So if the data is corrupted, you lost the data. Sector sparing. So it's like if sometimes some sectors becomes bad, you can no longer read and write data reliably from them. So in that case, you remap them. You forget about those and you remap that to transparently to another spare sector on the disk. And this is done by the controller transparently to the software. Sleep sparing. Now, if there is a bunch, if a sector goes bad, now the problem is that, now you no longer have sequential access. If you want to preserve sequential access, you may want to remap multiple sectors to preserve the sequentiality. And the last thing is track skewing. And here I have a figure for you what does it mean, track skewing. So this means that if the data is stored sequentially on nearby tracks, then I want to make sure that when I move from one track to another, I don't waste time. So here, these are the sectors on track one. So say I'm going to read on track one here, the head, I'm just finishing reading everything on the track one and I want move to track two. The track two is the one inside. Now, when I want to move, then the first sector on track one, I'm going to shift. So then this time, when I'm going to move the head to track one, by the time I moved, now sector 0 is ready to be read. If I don't do this, then while I move the head from one track to another, I miss the sector 0 and I need to wait for an entire evolution of the disk before I start reading it, right? So, and I'm going to end up with this slide. So this is an example of current hard disk drive. It's like 2020, 18 terabytes is a hard drive, 9 platters, 18 heads. Each platter has 2 sides, so one head for each side. 4 milliseconds average seek time. A sector is 4 kilobytes, 7,200 RPM, and so forth, and 270 megabytes per second maximum transfer rate. Cost 562. Now let's compare with IBM personal computer drive, the first drive. This was 86, okay? So the seek time is 10 times better, okay? The transfer time is 300 times better. But the capacity is 600,000 times better. And the cost, it's almost the same, 600,000 times better. So this is a progress we are able to get in 36 years. Okay, so it's quite impressive. Okay, so we are going to stop here. And next time we are going to start talking about solid SSDs. Thanks, everyone. Okay. Okay, I'm going to stop here and I'm going to answer the questions.